Hi, here we discuss about a project, a T8T-SRAM computing in memory macro for ternary deep neural network and Boolean logic computation. Here, the computing in memory CMOS based SRAM architectures have emerged as a promising solution for artificial intelligence, edge computing, Internet of Things, and low power embedded systems by reducing data movement between a memory and a processing unit, thereby improving a computational speed and energy efficiency. However, the existing SRAM CMOS designs, including a recently reported 28 nanometer implementation, still faces challenges such as a larger silicon area, increased transistor count and high power consumption, longer propagation delay, and complex hardware integration for Boolean logic and multiple accumulate unit, which means a MAC operation. Although the reported 28 nanometer in this paper, the T8T-SRAM architectures demonstrate improved computing capability for ternary neural network. There is still a need for a more compact and power efficient circuit implementation suitable for future VLSI systems. To address this limitation, this work proposes a compact T8T-SRAMs based architectures implementation using 22 nanometer CMOS technology in Ternary EDA environmental tool. The proposed work includes the design and implementations of an optimized AT-SRAMs, T8T-SRAMs, NAND, NOR, XNOR, and sense amplifier and MAC circuit, forming the essential building block for future SRAM CMOS architecture. The novelty of the proposed work lies in the implementing this optimized circuit block in a smaller 22 nanometer node while reducing a hardware overhead and improving a circuit compactness compared with the existing 28 nanometer implementation. The proposed design is prioritized to support a future low power and high density in-memory computing applications with a reduced silicon area and improved hardware efficiency. This circuit were designed and simulated and verified using Ternary EDA, and the performance was evaluated in terms of layout area, transistor count, propagation delay, and average power consumptions. The obtained results demonstrate that the proposed 22 nanometer implementations provides a compact and reliable and energy efficient hardware solution, making it stronger candidate for next generation SRAM based computing in memory systems and advanced VLSI application. Now we can verify the paper. So this work is a computing in memory macro unit using a T8T-SRAM, okay, which means a ternary 8 transistor SRAM architecture. The objective is to accelerate ternary neural network by performing computations directly inside the memory array, thereby reducing the von Neumann memory bottleneck architecture. Okay, the proposed macro supports 3 operating nodes in this paper: the conventional SRAM operations, Boolean logic operations, which means a NAND, NOR, XNOR, and ternary MAC operations. Okay, so unlike the previous architectures of this figures 1, there's SRAM CMOS design. This design separates the read and write paths, eliminates the read distributed problems while supporting a ternary wait and ternary activations. Okay, the core of this architectures, the initial architecture start with here. The figure 3, the circuit structures T8T-SRAM bit cells and readout circuit, and the truth table and ternary wait and ternary activation. Okay, so here they'll be used for 8 transistor SRAM architectures here. Okay, so using this 8 transistor SRAM architectures, the ternary MAC operations they'll be do, and this SRAMs also it will be support for the Boolean logic operations, and the third architectures it will become with the MAC architecture. Okay, so here the figure 5 it will be showing the illustrate the hold mode, write mode, and read mode operations of SRAM architecture, which means the flow of SRAM architectures, and figure 7 it will be showing the truth table for NOR logic, NAND logic operations. Okay, so this work now we can verify it in Ternary EDA. So this is the Ternary EDA architectures. Okay, so here the initial architecture start with SRAM. Okay, so here this is a SRAM architecture. Okay, so this is a simple 8T SRAM architecture. So once we have executed, we will verify the T-SPICE output and also the waveforms. Okay, so here you can verify the output. Okay, so here this is a BL and Q and RBL and RBLB, and this is a BLB and WL. Okay, so based upon the WL, the BL data, it will be written into the Q. Okay, so here you can verify it BL and Q. Okay, so it's just bypassing the data of BL. Okay, and the next architecture is T8T. Okay, so that is a ternary 8 transistors architectures. Okay, so this is a ternary concept. So normal SRAMs means it will be cover a binary operation. Okay, and this ternary 8 SRAMs means it will be cover the ternary based operations. Okay, so here you can verify the output. Depends upon the write line, the BL data, it will be switching to the Q. Okay, so that is a concept, right? But here the ternary operations, they will be using additional read operations in the circuit. Okay, here. Okay, so based upon the read operation, the RWL and RBLB0, RBLB1 or RBL and RBL2. Okay, so this kind of functionalities additionally we need to give here. Okay, so here the BLB, BL1, BLB, BL. Okay, so this kind of things. This is a test bench architectures. Okay, so based upon this, so here this is a ternary 8 architecture. Okay, so this output you can verify it here. Okay, so based upon this BL, the write line, it will be present for 0 and 1 and 2, which means a millivolt 400 and 500 and 600 millivolt. Okay, so it's varying the ternary output. Okay, which means a 0 1 2. Okay, or 0 1 minus 1. Okay, so whatever it is depends upon the voltage. Okay, so we can consider as it's a working as a ternary functionality. Okay, so here the ternary functionality, the BL at the time of 0, it's copied the one value. Okay, at the time of BL. Okay, so here you can verify it. So both it will be 1, it will be come with a high voltage, and both it will be 0, it will be caused to the 0 voltage. Okay, so this is the functionality happening here. So using this ternary function, the Boolean logic operations, it will be handled here. The NAND operation, this is a NAND gate. Okay, so here I'll run the NAND gate output. Okay, so here you can verify it. So NAND gate means it's inverse of AND gate output. So 1 1 means it's a 1 in the AND gate operation. So 1 1 means 0. Otherwise it's showing a 1. Okay, so here 1 1 means it's 0 in the output. This is a Q output, and otherwise it is showing a 1. Okay, so here we are given a 0 0 0 1 1 0 1 1 as an input. Okay, so this is a BLA and BLB. Okay, so same for NOR gate operation. Okay, NOR gate. So NOR gate means it's inverse of OR gate operation. Okay, so here you can verify the NOR gate operation. Okay, and this is a SA. Okay, so so it's just bypassing the data, depends upon the RBL. Okay, so here RBL data equal to 1010. Okay, so the Q data, it's just bypassing and improving the signal efficiency, because this SA architecture is working as a sense amplifier. And the next is a XNOR available and XR available, and the MAC architectures. Okay, so this is a MAC architecture. Okay, so here you can analyze the output, the MAC. Okay, so this is a MAC output. Okay, so this all output we analyzes in a T-SPICE. Okay, so and get a power results and delay results. Okay, and we updated the results in comparisons document. This is a comparisons results, and we updated a proposed abstract document. Okay, title, base paper abstract, improvement of the project, proposed title, proposed abstract, disadvantages, advantages, proposed with the related notes, and finally we come up with the literature's review and references. Okay, Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.